Good morning, everyone. It is my pleasure to introduce today's speaker, Professor Bibekananda Maji, as I was one of his students at IIT Gandhinagar. Currently, Professor Bibekananda Maji is working as an assistant professor in mathematics at IIT Indore. His core area of mathematical research in number theory with analytic number theory and special values of L functions being his prime area of interest. He did his undergraduation in mathematics in the Ramakrishna Mission Vidya Mandir, Calcutta University, while he completed his post-graduation from IIT Bombay. He did his PhD in the Harish Chandra Research Institute under the guidance of Professor Kalyan Chakrabarti. He completed his postdoctoral fellowship from IIT Gandhinagar under the guidance of Professor Atul Dikshit and Professor Aksha Vatwani. The awards won by him include Infosys Prize for Excellence in Research in Number Theory given by Harish Chandra Research Institute, Allahabad in 2016 and Best Paper Presentation Award in an international conference on number theory and graph theory, University of Mysore, Mysore in June 27-29, 2019. He is recipient of many fellowships such as Startups Research Grant, SERB in December 2020-22, National Postdoctoral Fellowship from SERB in 2017-2019, DAE Fellowship for the PhD program at Harish Chandra Research Institute, Allahabad. He has qualified CSIR NET exam for lecturership and junior research fellowship and cleared GATE examination for a PhD program in IITs. His research articles have been published by various journals and publications. He has also addressed around 20 talks in mathematics in various institutions. Thank you. Now I would like to request all the participants that if you have any doubt, please don't ask it during the lecture. Either you can write it in the comment section and we will address it. We will address them in the question answer segment, or you yourself can ask them in that segment. Now I would like to invite Professor Bibekananda Maji to start the lecture. Thank you.
Thank you, Devamshi, for your kind introduction. So let me share my slides first. Can you see the slides?
Yes, sir.
Yes, sir.
So I would also like to thank Professor Reddy and the young organizers of this program for their kind invitation. Okay, so today I'll be speaking on this few elegant proofs of the fact that the set of prime numbers is an infinite set. Okay, so all of us know that the set of natural number is an infinite set because so that all of you know. But the problem with the set of prime numbers, they do not have a pattern. They do not follow any single pattern like natural number follows. So, and the gap between any two consecutive prime numbers may be arbitrarily large. Okay, and due to this fact, you require a proper proof of the fact that the set of prime numbers is an infinite set. So in this talk, we'll see some proofs which was inspired from Euclid's proof. Okay, and at the end, I'll mention some more important proof, a deep proof, which may not be able to prove in this lecture. Okay, so let me begin with the definition of prime numbers. So our natural number p greater than 1 is said to be a prime number if it is divisible by only 1 and p. For example, 2, 3, 5, 7, these are all prime numbers, right? Now, let me state one important lemma. So given any n natural number, we can construct n consecutive composite numbers. Composite numbers are those which are not prime number. For example, 4, 6. So these are composite number. So this lemma is saying that given any n, any natural number, we can always construct n consecutive composite number. Okay. So let's see the proof. Proof is very simple. First, you construct this n1. So with this, using this small n plus 1 factorial plus 2. So the values of small n is bigger than equals to 1. So therefore, this capital N1 is obviously divisible by 2. Similarly, capital N2 is n plus 1 factorial plus 3, which will be also divisible by 3. Okay, and so on. So you define this last number n plus 1 factorial plus n plus 1. This is also divisible by n plus 1. So you can clearly see that all of these numbers are composite because it is divisible by 2. Is like n1 is divisible by 2 as well as it is divisible by n1, where n1 is bigger than 2. Okay, so you can check that all of these numbers are composite, and not only that, these are consecutive numbers. So you can see that n2 is n1 plus 1, right? So these are n3 is n2 plus 1, right? n3 is n plus 1 factorial plus 4. Okay, so these are all composite numbers, and they are consecutive numbers also. Now, see, so the lemma is saying that suppose this small n is 100. So in the sequence of natural number, you can find there are at some point there will be 100 composite consecutive numbers. So those are not prime numbers. So therefore, the gap between prime numbers can be arbitrarily large. So this lemma is saying that the gap between consecutive prime numbers can be arbitrarily large. So because of this fact, you need proper proof of the fact that the set of prime number is an infinite set. So when we start reading a basic number theory, this question comes first, and we start with Euclid's proof. Around 300 BC, he gave this nice proof. Okay, and over the next 23 centuries, many mathematicians have given different proof of this fact. Okay, so let me start with Euclid's proof. So this is known as also Euclid's theorem. The set of prime number is an infinite set. So the proof uses the method of contradiction. Okay, that means we'll assume that suppose there exist finitely many prime, then we'll arrive at some contradiction. So suppose there exist finitely many primes, p1, p2, pn. Then we construct a new number, capital N, which is product of all these pi's plus 1. And it is, you can clearly see that this capital N is bigger than all pi's, right? So now there are two possibilities can have, like this capital N number can be a prime number or it can be a composite number. So if in the first case, let us assume that suppose it is a prime number, then we are getting a new prime number, this capital N, which is larger than all pi's. But we have assumed that at the beginning there are finitely many primes. So therefore it is giving a contradiction to our assumption. Okay. Now in the second case, if N is a composite number, then it must have a prime divisor. But let's call that prime divisor as P. But our claim is that P cannot be one of these pi's. Okay, P is something new prime. Okay, P, this prime divisor of capital N will be something new prime other than these pi's. So let's see, if P equals to Pi for some I, then you see Pi divides capital N and Pi divides, of course, these products also. And if you know that one result, if P divides A and P divides B, then P divides A minus B. And using that fact, you can clearly check that P will divide 1, but which is a contradiction because every prime number is bigger than 1, right? So this proof is very simple. So therefore, we can conclude that a finite set cannot be the collection of prime numbers. So the set of primes must be an infinite set. Now, one question you may ask that, like, what will happen if we consider this capital N as a product of primes minus 1? So all of you can think about that. So maybe at the end, we'll discuss this. Okay. So one more thing I would like to point out, that this is giving a way of constructing. Suppose you have given like finite number of primes p1, p2, pn, and then constructing, writing a number capital N in this way, you are giving a way to construct a new prime. Okay, for example, now you start with 2. Okay, suppose p1 is your 2, like first prime is 2, then 2 plus 1 is giving you 3. Okay, then you have 2 and 3. Now suppose 2, you do the operation like 2 into 3 plus 1, then you are getting 7. Okay, now you have 2, 3, 7. Now you do the similar thing, 2 into 3 into 7 plus 1, which will give you 43. So again you are getting a prime. But in this way, again you construct like 2 into 3 into 7 into 43 plus 1. Then again you will get a number, but that number may not be prime. But the divisors will give you one new prime other than this 2, 3, 7, and 43. So that's how this process is telling. Okay. Now, Euclid's will see that this Euclid's idea has been how other mathematician has used Euclid's idea. Like inspired from Euclid's idea, there will see some different proofs. Okay, now let me talk about Fermat number. Fermat, Pierre de Fermat, French mathematician, he studied this number. Fn, he called this Fn as 2 to the power n plus 1, where n is any natural number, it can be 0 also. Now for n equals to 0, you can see that is f0 equals to 3, and for n equals to 1, f1 will be 5. For n equals to 2, it will be 2 to the power 4, which is 16 plus 1 is 17. So similarly, you can check that f3 is 257 and f4 is this number. And Fermat checked that all of these numbers are prime. Then immediately he conjectured that all the Fermat numbers are prime. But unfortunately, his conjecture was false. In 1732, Euler showed that F5 is product of these two primes. Okay, and not only that, after that, like after F4, till today, like there not a single Fn is known to be prime. Okay, like till now, people, mathematician proved, like found many Fermat numbers, but those all the Fermat numbers are composite. Okay, so I'll mention that. So Euler proved that every factor of this Fn must have of this form. Okay, some k is some integer, and then 2 to the power n plus 1 plus 1. So these are not like, it's not so immediate, but to prove this results. Okay. So later, this result of Euler was improved by Lucas. He proved that it can be improved 2 to the power n plus 2. So here, like Euler mentioned that it can be 2 to the power n plus 1, but Lucas said that it can be improved 2 to the power n plus 2. Okay. So let me say a few more things about Fermat numbers. So here I have given a table where factorization of Fermat number I have mentioned. You can see that F7 is completely factored in 1917. So the numbers is really huge, because it is a 2 to the power n plus 1, right? F11, it is a 617 digit number. So it has been completely factorized in 1988. As of 2021, like only from F0 to F11 have been completely factored. So we have already seen that F0 up to F4, those are prime number. But after F4, F5, F6 up to F11 only completely factored, and those are all composite numbers. But interestingly, one more observation you can see that it's coming like factorization is coming like P1 times P2 times P3 and so on. It's not coming like P square. We are not able to find a prime P such that P square is dividing some Fermat number. Okay, so I'll mention that. Okay, now let me mention some open problems related to Fermat numbers. So as I said, like as of 2021, like only 356 prime factors of Fermat numbers are known. Okay, and only 312 Fermat numbers are known to be composite. Okay, so now one may ask this: is Fn is composite for all n greater than 4? You can ask this question, right? So similarly, like Eisenstein asked this question that are there infinitely many Fermat primes? Yes, we have seen from F0 to F4, it is like prime. Then Fermat conjectured that all the Fermat numbers are prime. That was false because we found many Fermat numbers which are composite. But it may happen that like after certain stage, still Fermat numbers are prime. Okay, it may happen that infinitely many Fermat primes exist, but that is also not known. But yeah, one more question one can ask: that are there infinitely many composite Fermat primes, composite Fermat numbers? So that is also not known. Okay, and the last question you may ask: that does a Fermat number exist that is not a square free? So that means that is it possible to find a Fermat number which is divisible by some p square for some prime? But till now we haven't found such Fermat number. All the Fermat number we have seen, it's a product, it's a square free number. Okay, so these questions are very simple to understand, but it may be difficult to answer. But these are really active research areas. So those who are interested, they can see there is some nice book on Fermat number. So you can have a look at that book. Okay, now I'll mention Goldberg's idea of proving that infinitude of primes using Fermat numbers. So Goldberg wrote a letter to Euler around 1730 where he mentioned this proof using Fermat numbers. So he mainly proved that any two distinct Fermat numbers are relatively prime. So you consider GCD of Fn and Fm are 1 when m and n are distinct. Okay, so this will give us the infinitude of primes. So I'll mention how this will follow. Okay, so let's try to see that why this any two distinct Fermat numbers will be co-prime. So using this can be small exercise for all of you, like using mathematical induction on n, you can show that like this Fn are satisfying this property. So what you do to prove this Fn minus 2, you first try to see the pattern of Fn minus 2. Then once it is like Fn is defined as 2 to the power n plus 1, then when you are subtracting 2, then you will get basically 2 to the power n minus 1. Then you try to use basically a square minus b square formula, and then you divide that way. Okay, then you will get this product of all fi's where I will run from 0 to n minus 1. So I'm not going to prove this fact. This is very simple to check. Now, using this fact only, we'll prove that any two distinct Fermat numbers are co-prime. Let D be the GCD of Fm and Fn. Without loss of generality, let us assume that n is bigger than m. Now, you see, so this D divides Fn, and since n is bigger than m, so m will present in this product of Fi's. Fm will be present in this product because I is running from 0 to n minus 1. So therefore, D is dividing Fn as well as it is dividing this product. And therefore, it will divide the difference. So D divides 2. Hence, D can be 1 or 2. Right? But D equals to 2 is not possible, since all the Fermat numbers are odd. because it is 2 to the power n plus 1. So here is, at the first term is multiple of 2, right? So all the Fermat numbers are odd. So therefore, a d equals to 2 is not possible. Therefore, d must be equals to 1. So thus, we have proved that any two distinct Fermat numbers are co-prime. Okay. Now, you have how many Fermat numbers? You have infinitely many Fermat numbers. Okay. Now, let me say one thing. Like in this talk, suppose there are 50 students are attending this talk. Okay. Now, if we assign 50 students 50 distinct numbers, okay, so each one has like one number, and all of these numbers are co-prime. That means you do not have common prime divisor, right? So from each number, we'll get at least one prime. So from this 50 student, we'll get how many primes? At least 50 primes we'll get. Now, if we have a sequence like this Fermat sequence, so all of these numbers are pairwise co-prime. So that means they do not have any common prime divisor. So this is proving that we'll get infinitely many primes. From each one, we'll get at least one primes. And since we have an infinite sequence of numbers which are pairwise co-primes, so we'll have infinitely many distinct primes. So that is giving a proof of the fact that the set of prime is an infinite set. Okay, so that is what I have written. So now, not only for Fermat numbers, now you can understand that if you can create a sequence, a new sequence, where the terms are pairwise co-prime, then also you can say that infinitely many prime will exist, right? If we are able to create a new sequence such that the terms are pairwise co-prime, then also you can say that there will be we'll get infinitely many prime numbers. Okay, now let me mention a generalized Fermat number which has been studied by mathematicians. So here, instead of like at the beginning, Fermat number was defined as 2 to the power n plus 1, where a was 2 and b was 1. Now you can try to prove that like when a and b are co-prime numbers, then also this generalized Fermat number, they also give you like they will be also co-prime. Okay, so this also all of you can try this fact, try to prove this fact. Okay, so like for example, a equals to 2 and b equals to 3. Okay, so you are defining a new sequence 2 to the power n plus 3 to the power 2 to the power n, and then you try to find a relation like this. Okay, then from there you try to conclude, say that any two distinct generalized Fermat numbers are co-prime. Okay, so from there your result will follow. Okay, now I'll mention a proof by Philip Sider.